This episode is brought to you by Cisco Educational Premium. If you've been following, I hope we have been looking at the Planck scale. We have already introduced ourselves to it, explored it. We haven't explored the Planck length, Planck time, as well as their implications on our real world. Today, I want us to wrap everything up. Some conjecture that the structure of time need not remain smooth at intervals comparable to the Planck time. The Planck energy EP is approximately equal to the energy released in the combustion of the fuel in automobile fuel tank, 57.2 liters at that 4.2 megajoule per liter of chemical energy. The ultra energy cosmic ray observed in 1991 had a measured energy of about 50 joules, equivalent to about 2.5 times 10 raised to negative 8 Planck energy. Proposal for theories of doubly special relativity posit that in addition to the speed of light, an energy scale is also invariant for all inertial observers. Typically, this energy scale is chosen to be the Planck energy. The Planck unit of force may be thought as the derived unit of force in the Planck system if the Planck units of time, length, and mass are considered to be the base units. It is the gravitational attractive force of two bodies of one Planck mass each that are held one Planck length apart. One convention for the Planck charge is to choose it so that the electrostatic repulsion of two objects with the Planck charge and mass that are held one Planck length apart balances the Newtonian attraction between them. Some others have argued that Planck force is on the order of the maximum force that occurs between two bodies. However, the validity of these conjectures has been disputed. The Planck temperature Tp is 1.41678,416 times 10 raised to 32 Kelvin. At this temperature, the wavelength of light emitted by thermal radiation reaches the Planck length. There are no known physical models able to describe temperatures greater than the Planck temperature. A quantum theory of gravity would be required to model the extreme energies attained. Hypothetically, a system in thermal equilibrium at the Planck temperature might contain Planck scale black holes, constantly being formed from thermal radiation and decay via Hawking evaporation. Adding energy to such a system might decrease its temperature by creating larger black holes whose Hawking temperature is lower. Physical quantities that have different dimensions such as time and length cannot be equated even if they are numerically equal. Like 1 second is not the same as 1 meter. In theoretical physics, however, this problem may be set aside by a process called non-dimensionalization. The effective result is that many fundamental equations of physics, which often include the sum of the constants used to define Planck units, become equations where these constants are replaced by 1. Examples include the energy momentum relation becomes E square is equivalent to C square bracket all of that raised to 2 plus PC square, which become E square is equivalent to M square plus P square, and the Dirac equation, which becomes as shown. As we have already looked at, Planck units are derived by normalizing the numerical values of certain fundamental constants to 1. These normalizations are neither the only ones possible nor necessarily the best. However, the choice of what factors to normalize among the factors appearing in the fundamental equation of physics is not evident, and the values of Planck units are sensitive to this choice. The factor 4 pi is ubiquitous in theoretical physics because in three-dimensional space, the surface area of a sphere of radius r is 4 pi r square. This, along with the concept of flux, are the basis for the inverse square law. Gauss law and the divergence operator applied to the flux density. For example, gravitational and electrostatic fields produced by point objects have spherical symmetry, and so the electric flux through a sphere of radius r around a point charge will be distributed uniformly over that sphere. For this, it follows that a factor of 4 pi square will appear in the denominator of Coulomb's law in rationalized form. Both the numerical factor and the power of the dependence on R would change if space were higher dimensional. The correct expression can be deduced from the geometry of higher dimensional spheres. Likewise, for Newton's law of universal gravitation, a factor of 4 pi naturally appears in Poisson's equation when relating the gravitational potential to the distribution of matter. Hence, a substantial body of physical theory developed since Planck's 1899 paper suggests normalizing not g but 4 pi g or 8 pi g to 1. Doing so introduced a factor of 1 on 4 pi or 1 on 8 pi into non-dimensionalized form of the law of universal gravitation, consistent with the modern rationalized formulation of Coulomb's law in terms of vacuum permittivity. In fact, alternative normalizations frequently preserve the factor of 1 on 4 pi in the non-dimensionalized form of Coulomb's law as well, so that the non-dimensionalized Maxwell's equation for electromagnetism and gravitoelectromagnetism both take the same form as those for electromagnetism in SI, which do not have any factors of 4 pi. When these apply to electromagnetic constants, E naught, this unit system is called, and I quote, rationalized. When applied additionally to gravitation and Planck units, these are called rationalized Planck units and are seen in high energy physics. The rationalized Planck units are defined so that C is equivalent to 4 pi g, which is equivalent to reduced Planck's constant, which is equivalent to E naught, which is equivalent to Kb, which is equivalent to 1. There are several possible alternative normalizations. In 1899, the Newton's law of gravitation was still seen as exact, rather than as a convenient approximation, holding for and accord small velocities and masses. The approximate nature of Newton's law was shown following the development of general relativity in 1915. Hence, Planck normalized the gravitational constant g in Newton's law. In theories emerging after 1899, g nearly always appears in formulae multiplied by 4 pi or a small integer multiplied thereof. Hence, a choice to be made when designing a system of natural units in which, if any, instances of 4 pi appearing in the equations of physics are to be eliminated for the normalization. 1. Normalizing 4 pi g to 1 and therefore setting g to be equivalent to 1 on 4 pi. Gauss law for gravity becomes phi g, which is equivalent to negative 4 pi m in Planck units. Something else is that it eliminates 4 pi g from the Poisson equation. Also, it eliminates 4 pi g in the gravitoelectromagnetic GM equation, which hold in weak gravitational fields or locally flat spacetime. These equations have the same form as Maxwell's equations and the Lorentz force equation of electromagnetism, with mass density replacing charge density and with 1 on 4 pi g replacing epsilon naught. It normalizes the characteristic impedance Zg of gravitational radiation in free space to 1, normally expressed as 4 pi g on C. It also eliminates 4 pi g from the Bekenstein-Hawking formula for entropy of a black hole in terms of its mass, mbh, and the area of its event horizon, abh, which is simplified to SBH is equivalent to pi, ABH is equivalent to mbh square. 2. Setting 8 pi g to be equivalent to 1, and therefore setting g to be equivalent to 1 on 8 pi. This would eliminate 8 pi g from the Einstein field equations, Einstein-Hilbert action, and the Friedmann equation for gravitation. Planck units modified so that 8 pi g will be equivalent to 1 are known as reduced Planck units because the Planck mass is divided by root 8 pi. Also, the Bekenstein-Hawking formula for the entropy of a black hole simplified to C-square educational premium is a section of C-square educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.